All right. Let's see if this is, maybe I need to zoom this guy in a little bit more. Okay, let's start from the beginning. Okay, this is 2h. The lengths of two displacement vectors, delta r1 and delta r2, are 6 meters and 10 meters respectively. You're told that their scalar product is negative 36 meters squared. They want to know the angle between the vectors delta r1 and delta r2. And they're being kind of cute about it. They're saying one possible angle because you could have several angles. All right, so remember you had a homework problem like, maybe a couple homework problems like this. The dot product you can calculate in terms of, right, the dot product formula is the dot product between two vectors A and B is the magnitude A times the magnitude and B times the cosine of the angle between them. And so if you know the dot product, then you can, and you know the magnitudes of the vectors, you can get the angle. Okay. So we have dot product of delta r1, delta r2 is, we're given it's negative 36. It's equal to the magnitude of r1 and r2 times cosine of theta. We're told magnitude of r1 is 6, magnitude of r2 is 10, and so we have 6 times 10 times cosine of theta. So now we can solve for cosine of theta. It's negative 36 divided by 60, and that's negative 0.6. And so you get that the theta would be, well, it can either be 127 or negative 127. And they were being kind of cute about it and saying they want negative 127 for the answer. Okay. Any questions about this? Everybody good? Okay. Let's do another dot product type formula. So a constant force F is 18 I hat plus 12 j hat with units of newtons. It's applied to an object with a mass of 5 kilograms. The force causes a displacement delta r, which is 2.0 times I hat times m. And you want to know the work done by the force. Okay. So the work done by a constant force is F dotted with the displacement delta r. And so we have this formula for the dot product in terms of cosines of angles, but we also have the formula that it's going to be Fx delta Rx plus Fy delta Ry, right? Just you multiply the x components together, you multiply the y components together, and you add them together. Okay. And so we have 18 is the x component of F, and 2 is the x component of R. And then for the y component, we have 12, and then we have 0 for the y component of delta R. Okay. Everybody's got that? And then you add these together, 18 times 2 plus 12 times 0, this is nothing, so you get 36 joules of work. Okay. Any questions about this? So these dot products are pretty straightforward. You just have to, there's two formulas. Either you have a formula with magnitude of A times magnitude of B times cosine of the angle, or you have AX times BX plus AY times BY, and if there's a Z, then AZ times EZ. All right, let's go on. Okay, here's a problem on a ball bearing that's released from rest in a tank of water. Okay, this sounds kind of complicated, but you have all the tools to solve this problem. So a 0.25 kilogram ball bearing is released from rest at the surface of the water in a tank of water, as shown in the diagram. So it's released here from rest. After it falls 2 meters, so it's a pretty deep tank, so you can think of maybe a swimming pool or something. After falling 2 meters in the water, its speed is 5 meters per second. The question is, the amount of work done by the water on the ball bearing is what? Okay. First of all, Um, by the way, is it clear to everybody what the sign of the answer should be? Does everybody have a good sense that it should be negative? Does that make sense? Okay. If it's not clear, it just intuitively the ball is going down, right? And just think, we didn't really talk that much about water, but we talked about drag forces, right? It's going to try to push it upwards as it's flowing down. So if the force of water goes up and the displacement is down, then the work is going to be what, positive or negative? It's going to be negative, right? It's the opposite direction. So it's going to do negative work. Just like friction, whenever the question is how much work does friction do, it's going to do negative work. It's going to take energy out, mechanical energy out of the system. Okay. All right, but that doesn't tell us the answer. So let's figure out how to get this. Now, by the way, there are two different ways to do this problem. I'm going to show you how to do this problem using the work energy principle. Remember, the work energy principle is that the net work done by all forces is equal to the change in the kinetic energy. All right? Or you can use the work done by non-conservative forces, the change in the mechanical energy. Right? They sound like different things, but in the end, the equations end up being pretty much exactly the same. Okay, so don't get hung up on which principle, which theorem, which thing do I use to solve the problem. Just solve the problem. Okay, so here we go. Work energy principle. All right. We know, let's figure out, so the idea is that we're going to figure out the change in, okay, so this is the work energy principle, that the work done by all the forces, or the work done by the net force, in other words, just get the work of everybody put together, is equal to the change in the kinetic energy. And then what we're going to do is we're going to figure out how much work, well, first of all, we'll figure out delta K, and then we'll figure out how much work gravity does. If I know how much work gravity does, the rest will be the work done by the water. Does that make sense to everybody? Okay, so let's first figure out work done by gravity. So work done by gravity. I have the force Fg that's going down, like this, and the displacement is d like this, so Fg is like this, displacement like this, d. They point in the same direction, so when I do Fg dot d, I just get the magnitudes multiplied together with the cosine of 0, or just 1. Okay. So let's figure out the force of gravity. Fg is equal to m times g. M is 0.25 kilograms, right there. And g is 9.8, so I get 2.45 newtons. All right, now I have then, so Fg is 2.45 newtons, and then the distance d is 2 meters, so I multiply them together and I get 4.9 joules. That's the work done by gravity. Okay, work done by gravity. Now, I said I'm going to use this over here. I need delta K. Maybe I should have started there, but it doesn't matter. So the ball bearing starts from rest, so the initial kinetic energy is 0. By the time it falls down here, it has a speed of 5 meters per second. So, and the mass is 0.25, so I can get the change in the kinetic energy. It'll be 1/2 0.25 times v final squared, so 0.25 times 5 squared, and that comes out to 3.13 joules. The initial kinetic energy was 0, so that's why this is the change of the kinetic energy. Okay, any questions about any of these steps so far? So you could imagine a question, what is the change of the kinetic energy? What is the work done by gravity? That could be another question in a different version of the problem. Okay, so that's how you would calculate these things. Now, in order to calculate how much work is done by water, we say the work done by water is the work done by all the forces, the net force, or the sum of all the forces, minus the work done by gravity. Okay. All right, but then the work done by the net force is just delta K, which we've calculated. So 3.13 joules minus the work done by gravity, 4.9 joules, and I get minus 1.8 joules. Okay. Any questions about this? All right. I know probably some of you don't really like this work energy thing because it's a little complicated. So if you want to do the other way, you would say the work done by the non-conservative force. You would go like this. You'd say the work done by water. So let me just sketch out how that would go. You'd say the work done by the water, which is a non-conservative force, is equal to the change in the mechanical energy. So the change in the kinetic energy, change in the potential energy. All right? That's how maybe most of you would want to do this problem. And then you get the change in the kinetic energy, and you do the same problem that I did here, and you get 3.13 joules. Okay? And then you calculate the change in the potential energy, and then you'd say it starts here and it drops down by 2 meters, and so you would end up getting that the change in the potential energy is minus 4.9 joules, and then you would end up with minus 1.8 joules as the answer. Okay? Probably most of you prefer this. It's a little easier. Okay. Any questions about this? Either way is perfectly fine. Okay, the next problem is more of a quiz 3 problem, so maybe I'll skip it. This was about momentum and force. The force was the time derivative of the momentum, so let's go on to a power problem. So the problem is a horizontal force of 800 newtons is required to push a stalled 1,200 kilogram car along a horizontal road at a speed of 3 meters per second. So given that horsepower is 746 watts, the power expended is what? Okay, so this is just a straightforward problem with power. By the way, all of the questions with power are typically pretty straightforward. You just calculate work, you divide by time. Okay? That's all you have to do. So, well, actually I lied. In this case, they tell you the speed. So in this case, the formula is the force times the dotted with the velocity. So the power is force dotted with velocity. Okay, that's the work, the power done, exerted by a constant force. So the force is 800 newtons, and the direction of the velocity is the same as the force. And so we just multiply 803 to times 3, and that comes to 2,400 watts. But they want to convert this into horsepower, so you divide by 746, okay, and you get 3.2 horsepower.
That conversion is going to be on the formula.
Yeah, you're not expected to know that. That's right. We don't expect you to know that number. Okay. Any questions? Okay, let's go on. Springs. Okay. A 0.5 kilogram object is resting on a horizontal frictionless surface and is compressing a spring by 0.12 meters. When the object is released, the spring gives it a speed of 0.20 meters per second. The question is, the spring constant of the spring is equal to what? Okay, so if this is conservation of energy, delta K plus delta U is equal to 0, or maybe this is the way I wrote it. What year was this? This was 5 years ago or 6 years ago. The way I liked this, students didn't like the way I wrote this, so that's why these days I always write it as K initial plus U initial is equal to K final plus U final. Students preferred writing it this way. Okay. Anyways, the initial U, so UI, is 1/2 kx squared. They give you, actually they don't give you k, but they give you x. Okay, so they tell you that x is 0.12 meters. So I take 0.12, square that, okay, and that comes out to 0.0144. And then you divide by 2, and you get 0.0072 times k, which you don't know yet. Let's see, then U final, that's when the spring has released the ball, so it just lets go after it reaches. If you just think about what's going on, after it gets to the equilibrium point, the spring then will not the spring is pushing the ball. It doesn't also pull the ball in as well. Okay? So once it gets to the equilibrium point, the ball dislodges from the spring, and so the spring doesn't have any potential energy anymore. So if you're worried about exactly what's going on with the spring, when you squish a spring and it lets go, at the final point, there's no potential energy in the spring. Okay, that's just a very simple thing. All right, so U final is equal to 0, and because everything is horizontal, there's no gravitational potential energy we have to worry about. It's all the same. Okay, then for K final, the final kinetic energy, we have 1/2 1/2 times the mass, which is 0.5, times 0.2 is the speed squared, so 1/2 mv squared, and that comes out to 0.01 joules. Okay, and then the initial kinetic energy, it starts from rest, and it is equal to 0. I'm sorry, I went in this funny order. I went to U initial, then U final, then K final, then K initial. I should have gotten it in a better order. Okay. So now we have that the K. Let's just do this with Ki plus Ui is equal to K final plus U final. All right. And so now we just collect everything together. So we have U initial is 0.0072 times K. So 0.0072 times K. And K initial is equal to 0. And then K final is equal to 0.001010 joules. Okay. And then U final is also equal to 0. So that's what I have written here. Oh, you can't see that, sorry. And so now I can solve for K. Take 0.0010 divided by 0.0072. No, I have too many zeros here. Be like that. 0.010 divided by 0.0072, and you end up with 1.4 newtons per meter. Okay. Questions? Okay, let's try to find it out. Yeah, here it's this. It's written with these annoying s's, but yeah, okay. 1/2 k x squared. Questions? Other questions? Okay, let's go on. Okay, the next one is these free response problems. So in this course, the students had these free response problems where we would grade them by hand. This is actually pretty good, but it took forever to do this. It's okay. It's a little bit weird what they're asking the students to do here. So you're supposed to show your work, and they want you to. Here, I'll just show your work the following problems, provide enough detail of what you're doing, take all the steps, and then partial credit will be given for blah blah blah, write legibly, and then so you're just supposed to. Actually, this is not so bad. There's another one where you're supposed to set up equations without the numbers or something. Okay, this is. I thought it was going to be weird, but it's not that weird actually. Not that weird. So I take it back. It's just a straightforward problem. Okay, a child of mass m equals 50 kilograms slides down a frictionless swimming pool slide starting from rest, okay, as shown in the diagram. Consider the child as a particle. Okay. Take the zero of potential energy to be the water level. Right. Determine the initial gravitational potential energy of the child. Okay, so let's just calculate the gravitational potential energy of the child. So we know the child relative to the water level is at a height of 5.2 meters. So the formula for the gravitational potential energy is just m times g times yi. Okay. So plug in, the mass is 50 kilograms, 9.8 is G, 5.2 is the height, and so we get 2,548 joules. Any questions about this? It's not so hard, right? Now the next one. Okay, so this part is a little bit unusual. You're supposed to write down the equation without solving anything. So this part is write the equation for conservation of mechanical energy as it applies to the motion of the child. Write this in symbols M, etc., defining each symbol used. Okay, conservation of energy is K initial plus U initial is equal to K final plus U final. Let's take Yi to be the initial height, Y final to be the final height, and let's take V final to be the final speed. Okay, since the initial speed is 0, we don't need to define the VI as just 0. Okay, so then over here on the initials, K initial 0, UI is MGY initial, K final is MGY final, and then UF is the so, okay, sorry, I should put them in the other order. It's kind of strange that I did it that way. So the K final is 1/2 MV final squared, and U final is MGY final. Okay? Any questions about that? All right, let's go on. Now, they want you to do something with this equation. So use conservation of mechanical energy to determine the final speed of the child at the bottom of the slide. Okay? So now we have MGY initial is this value we calculated up above, 2,548 joules. And so we have 2,548. Then we have that, okay, I kept it in this order, so MGY final. So M is 50, G is 9.8. Y final, this height, you can't see it, is 0.92. So this child is not exactly at the water at the end of the slide, but 0.92 meters above the water. Okay. And so plugging in the numbers for this guy, okay, so I didn't talk about this one yet. I also have 1/2 MV final squared. The mass is 50 kilograms, so we have 1/2 50 V final squared. So multiplying these three numbers together gives 450.8. Multiplying 1/2 and 50 gives you 25. So we have, and then subtracting 2,548 by 450.8, and then dividing both sides by 25, you get the final squared is 83.9 meters squared per second squared. Taking the square root of both sides gives 9.16 meters per second. Okay. Any questions so far? All right. So now the problem keeps going. Now the question is, now suppose that friction in the slide reduces her speed at the bottom of the slide to 6.1 meters per second. Okay, calculate the work done by friction. Okay, so the work done by friction is a non-conservative force, so the work done by the non-conservative force is the change in the mechanical energy. Or in other words, delta E mechanical, which is delta K plus delta U. Okay, so we're just going to calculate the work done by friction by calculating delta K plus delta U. So delta K is the change in the kinetic energy, delta U is the change in the potential energy. And sorry, for some reason I keep trying to screw you up by reversing the order of the U and the K. Sorry about that. So the yeah. Okay. I don't know why I did that. Somehow I kept changing my mind where things should go. Okay. So K final is going to be 1/2 times the mass 50 times the final speed, which is 6.1 meters per second squared. Okay. The initial, right? We also have to subtract the K initial, but that's equal to 0 because it starts from rest. She starts from rest. Okay. Now then we have to get the U final minus U initial. Okay. So U final, those numbers remain the same. That's what we had before. We found that we have, you can't see that, 450.8 is the U final, and the U initial we calculate up here, 2,548. Okay, so we have 450.8 minus 2,548. And so we end up putting all these together. You get minus 1,170 joules. Questions about that? And then the last part was just calculate her mechanical energy at the bottom of the slide. So her potential energy at the bottom of the slide was 450.8. Okay, once again, I screw you up by doing the reverse order. I don't know what was wrong with me. And then you have 1/2 mv final squared. So 1/2 50 times 6.1 squared, you get 1,380 joules. Right. Any questions about this? Everybody can do this? No sweat? Okay. Next problem. Two small carts are set in motion in a collision course toward each other on a frictionless horizontal track. Cart 1 has a mass of 0.4 kilograms and is initially moving in the positive x direction with velocity v1 is equal to 3 meters per second. Cart 2 has a mass of 0.2 kilograms and is initially moving in the negative x direction with v2 is equal to minus 3 meters per second. Velcro on the ends of the carts makes the collision completely inelastic, meaning they stick together. And after clotting, the cars move together as a unit. Okay? So this is it's an inelastic collision. So when I say inelastic, that means the kinetic energy is not the same at the beginning and the end. If it was elastic, it would be the same at the beginning and the end. But no matter what the collision is, if it's an isolated system, momentum is good. Okay, just keep that in mind. Momentum works. You don't have to say anything except for the fact that it's an isolated collision, momentum will work. Okay. All right, so we have 0.4 kilograms going to the right with 3.0 meters per second. We have 0.2 going to the left at 3.0 meters per second, so that's why I have minus 3.0 for the x component. So I take this to be positive x. All right, so we're going to calculate the initial momentum. So the initial momentum, we're doing momentum conservation. So it's the mass times the velocity component. So 0.4 times 3.0. Then for the other mass, I have 0.2 times negative 3.0. And then that adds up to 0.6 kilogram meters per second. Okay. By momentum conservation, so momentum, never wrote that down, conservation. This must be equal to the final momentum. Okay, so P final is equal to this as well. And P final is equal to the mass of both of them, M1 plus M2 times V final. But the sum of the two masses is 0.4 plus 0.2 is equal to 0.6. I must have gotten tired at this point and stopped writing things down. And then, so now I can solve for V final. It'll be this 0.6 divided by, again, 0.6, and so you get 1 meters per second. Okay. Any questions about this so far? So conservation of momentum gives you the final speed of the carts when they're stuck together. Now we're going to calculate the total kinetic energy of the two carts after the collision. Okay, so we have both carts stuck together, all right? And this, as a unit, is 0.4 plus 0.2 equals 0.6 in mass, and it's moving with a speed of 1 meters per second. So to get the kinetic energy, final, will be 1/2 times the mass, which is 0.6, times the speed, which is 1 squared. And so it comes out to 0.3 joules. Okay. Any questions about this? Good. Now then they ask, determine the mechanical energy lost in the collision. So let's figure out what is the mechanical energy in the beginning. So in the beginning we had a mass of 0.4 moving with 3 meters per second, and we had another one moving negative 3 meters per second like this, with a mass of 0.2.
You're off the screen this side.
Okay, thank you. And so now we have 1/2 0.4 times 3 squared is the kinetic energy of this guy here. And then we have the kinetic energy of this guy is 1/2 times 0.2 times negative. If you want to put a negative here, it just drops out though. Negative 3 squared. And so that comes out to 2.7 joules. Now we can compare the two. This is the initial. This is the final. So the change is defined as the final minus the initial. So 0.3 minus 2.7, you end up with negative 2.4 joules. Okay. So you lose this energy, mechanical energy. It goes into something like heat. Question? Okay, yeah. So for the kinetic energy, for the momentum, the signs make a difference. Okay, but for the kinetic energy, the formula is 1/2 mv squared, and the squaring gets rid of all the minus signs, so they always add up. Other questions? All right. That's all I wanted to cover from this test. So now let's finish it off with a quicker question. Okay, a pole vaulter has a mass of 51 kilograms and approach speed of 8.1 meters per second. Okay, but by the way, we're idealizing things. I'm not going to write all the details down. So if you don't know what pole vaulting is, if you're not familiar, you have this big stick, you run with it, and you plant it, and you bend the stick, and then you lift your body up. Okay? So we're going to assume that the pole is really, really light compared to the person. Okay, so we can aim it like that. So don't worry about the pole. Don't worry about air resistance, friction, all that stuff. Okay? So the approach speed is 8.1 meters per second. When she is directly over the bar, her speed is 2.0 meters per second. And neglecting all this other stuff I mentioned, okay? How high is she raised? Has she? How high has she raised herself? Okay. She starts from the ground with her feet on the ground. Think about her center of mass. We haven't talked about center of mass, but how high does her body center? Think of her. Okay, if you try to simplify her, think of her as a point particle. Okay, starting from the ground, how high does that point particle go up? And so now the choices are 1.92 meters, 9.17 meters, C is 4.86 meters, D is 3.14 meters, E is 4.21 meters. Okay, this is, I guess maybe I should zoom out so we can see it all a little bit easier. Okay, I'll open up the polling now. So just quick for material. There aren't that many energy conservation sort of things where dot products or power. So if you get these down, you can do very well because they're all kind of great. I'll give you another 30 seconds. All right, anybody need more time? Yes. Pretty good. If you haven't made a choice, go ahead and make a choice. All right, let's see what people said. All right, a lot of people say D, so let's take a look. Conservation of energy. All right, if in doubt on quiz 4, the answer is we have to get conservation of energy to work. Okay. So we have the K final plus U final is equal to K initial plus U initial, or vice versa, doesn't matter. So let's look at what we have for initial. We have that K initial is equal to 1/2 mv initial squared. And so we have 1/2 times the mass, 51, times initial speed, 8.1 squared. That comes out to 1,673. The U initial is, let's say we start from the ground, that's y equals to 0. So mgy initial, this is equal to 0, so that's 0. And for the final, we have K final is equal to 1/2 mv final squared. And that's equal to 1/2 51 times 2.0 squared. And that comes out to 102 joules. And the U final is equal to m times g times y final, which we don't know. Okay, so we have 51 for the mass, 9.8 for g, and then y final, and that comes out to about 500 y final. And now we have K final plus U final equals K initial plus U initial. So we have 102 plus 500 Y final is equal to 1,673. And then we can solve for Y final, and it comes out to about 3.14 meters. Okay. Any questions about this? All right. If not, get working on your homework as due Sunday. It's kind of tough. If you have questions, send me an email. Okay, I'll see you guys tomorrow.